continue talking about path sampling techniques. We talked about transition path sampling and TIS, RETIS yesterday. Today, we'll talk about forward flux sampling, which I'm going to call FFS, and then contour forward flux sampling, which I'm going to call CFFS. And we'll do essentially the same strategy that we had yesterday. I'll give you a brief introduction to the methods. Then we'll have a hands-on activity in which you can play around with different potential energy surfaces and various other parameters that are involved in the calculation. Then we'll have a break, we'll do CFFS, another hands-on, and then we'll spend a little bit of time in talking about how we can run these calculations on HPC. So far, you've looked at it in Jupyter notebooks, but when you're running these for real systems, for more than just toy systems, you're going to run them on HPC. And unlike what we saw at Metadynamics and stuff, you don't have a software readily available to just run them. Although there are these softwares now being started to develop, but it's still not as straightforward as, let's say, running Metadynamics by just patching with Plume. So we'll go over a little bit of that, and we have some scripts also that you can run, but they'll take time, so we'll probably not see all of the results today. And then we'll end with a Q&A session after a quick wrap-up. All right, so we started with this problem, right? I like this graphic to show we really are in this valley, we want to get to that valley, and we said there are many different ways of doing it. One is I can select a path and then force my system to go through that. That's kind of what most free energy methods do. And then otherwise you can use path sampling, where you sort of try and explore the path space and you do a Monte Carlo in that path space. So we learned about 3 different methods yesterday. This is just a reminder slide. But whichever method in this that you're using, you're doing a Monte Carlo in the path space. Now, for forward flux sampling, you kind of continue along the same stream, except if you remember from TPS, TIS, and RETIS, you did a back propagation of the path after you selected a time slice and did a shooting move. But in forward flux sampling, you will no longer do that back propagation. You actually just do one forward direction propagation. Because of this quality, you can also use this method to study non-equilibrium systems where you have driving forces and stuff. And this is one of the only methods that's there where you can that you can use in this path sampling sort of family for studying non-equilibrium systems. And so what you do in forward flux sampling is the following. So as you do with TIS, you decide the transition you want to observe. You're going to divide your phase space into a basin A and a basin B. And then you're going to specify some interfaces in between A and B. And this is something that we did yesterday for TIS as well. Then you're going to run a simulation in basin A, and there'll be a long simulation. This can be an MD simulation, a Monte Carlo simulation, whatever you want to use for your sampling. And what you'll find is all of the first crossings that cross this first interface, right? And what I mean by first crossing is that in this trajectory, this path is coming directly from A. It hasn't gone outside of this interface, gone back to A and stuff. It's coming directly from A. And then from these configurations, what you do in forward flux sampling is shoot many different simulations. And basically, when we say shoot many different simulations, in case of MD, what you're saying is you're going to take the point, randomize the velocity, and run a simulation. And you'll do this for every configuration point n number of times. And what you'll observe is most of the trajectories go back to A, and some will move forward to the next interface. You pick those configurations, and then you run several simulations. Some will move forward, many will go back. And then you just keep doing this process till you get to state B. And so this, you can think about this as climbing a ladder one step at a time, right? And because we only shoot forward, this is what I meant by saying that we only do a forward propagation. And then that's essentially what allows you to also use this method to study non-equilibrium systems. And then for your rate calculation, you'll essentially use the same equation as you did yesterday for TIS. You're going to calculate the rate by multiplying a flux with the probability of starting in A and going all the way to B. And this probability of going from A to B, you're going to calculate as the product of these smaller probabilities of going to the next interface starting from the previous interface. The flux is calculated as number of first crossings that you get in this long simulation or divided by the length of the simulation, and you can normalize by volume as well if you want to do it on a per volume basis. And what I mean by first crossing, I'm showing you a few examples here. again, just to emphasize on that, is you're talking, when you run a simulation, you're talking about the first time that the path crosses the milestone that you're interested in. So in this case, going from basin A to the first interface, you're going to see when it crosses from basin A to the first interface. In this case, you're looking at going from interface 1 to interface 2. So you look at this path, and this is where it crosses the first time, the interface 2. So that's my first crossing. If it weaved around and then recrossed the path, the interface again, we won't use that at all. In fact, in most cases in the application, as soon as you see the first crossing, you'll try and terminate the trajectory. You won't even propagate it any further. So you're really only looking for first crossings in the whole thing. And then the second term, of course, is this probability of going to the next interface starting from the previous one. And the way you calculate it is simply by taking the ratio between the number of successful crossings you get over all the simulations that you do at a given interface. So if I were to shoot 100 simulations here total from, let's say, interface 2, and 50 sort of cross to interface 3, then that'll be 50 over 100. And I can then multiply each of these probabilities, get the total probability, multiply it with the flux, I get the rate. And to get the transition path ensemble, what I can do is I can go backwards, right? I can take this fragment that connects the last interface to basin B, join it with a fragment that connects the last but one interface with the last interface, and so on and so forth. And if I connect all of these trajectory fragments, then I get an entire path connecting A from B, and I can get a collection of these paths, and then that's my transition path ensemble. And once I have this, I have all of the information I need to do mechanistic calculations. All right, so there are many different ways that you can implement this. I'll just give you an idea of how we implement it. So when I just started working on this method as a postdoc, actually, I was really trying to automate it because I didn't want to, go in and decide the next interface and then, terminate my trajectories by hand or anything. And the second thing I didn't want to do is go in and modify any of the software I was using to propagate the system. So at that time, I was using Chromax. And to be able to calculate an autoparameter and decide whether it's reached the next interface and if I should terminate the simulation, often you would need to do some calculation on the fly. And then that usually required a change in the software at that time, which I didn't want to do. So I developed this sort of algorithm here, and this is what we do. We run some simulations for a specified time at a given interface. You calculate the statistics of the autoparameter. So what I'm going to do is I'm going to look at all of the trajectories that I have. I'm going to create sort of a histogram of the autoparameter values that I'm sampling. And then based on that, I'm going to decide the next interface. So now we are deciding the interfaces on the fly. And I'm going to decide it based on saying I want enough number of configurations at the next interface, but I also, and I don't want to place it too close or too far, right? So this is what allows me to do that. What that enough number of configurations at an interface are is a parameter you have to decide based on your system. And then I go back once I know what the next interface value is and evaluate the fate of each of these trajectories. And they can have three fates, right? They could have reached the next interface, which I've decided here. If that's the case, I store the configuration and the path. They could have gone back to the basin A. In that case, I just discard it. Or they could have remained incomplete, which means that they haven't run long enough to commit either to the next interface or to go back to the basin. So I will just run them longer till they come to some fate. Now, in some cases, these incomplete ones are really a small number. So for practical purposes, you can also choose to ignore it, but that's a very nitty-gritty detail. Right, so this is how you would run it, and this is one way of running it. All right, so as you can imagine, because everything starts from the first interface in forward flux sampling, the sampling at the first interface is very essential. And you have to be very careful about it. If you do a bad job of sampling at that first interface, basically everything else will not work out well. And until you complete forward flux sampling, you can't tell whether it's good or bad sampling. So that makes it a challenge also. So we and other people in the field have been developing methods or metrics to see how well are we sampling at that first interface. So I'm showing you a few parameters here. So one thing that you can do is, because you use one order parameter to propagate your system, you want to make sure that at any given interface, it's able to sample in the orthogonal directions, right? So that will ensure that you have a diversity of configurations. So that's what we are looking at here. So this is for an example of a Lennard-Jones system that undergoes liquid to solid transition. So it's going to nucleate, and we use an order parameter of some nucleation size. And what we're doing is we are looking at the first interface. These are our configurations and how are they spanning in the orthogonal space. And the two order parameters that we are using to characterize this orthogonal space is another measure of the crystal size and the structure of the crystal, for example, right? And these blue points here are independent simulations where we've done a lot of basin sampling, and we have looked at what the spread of these two parameters is. And now by these red points, which are the configurations we get at the first interface, we are overlaying on that independent simulation and seeing if our spread is good enough, or does it match well with that independent one. And because it does, we feel confident about that sampling of the first interface. The other thing that you want to make sure of is that your configurations that you get at the first interface are decorrelated. And so we're back to this question of decorrelation. So if you remember here, when I was talking about picking these first configurations, you can imagine that what might happen is that you end up in a trajectory which does this, right? If it crosses so quickly with, in a small span of time, you can kind of guess that these crossings would probably be very correlated. And so you don't want to use a whole bunch of these and then just have one or two decorrelated configurations. You want to actually get a good spread of the configurations, which would help you get more independent samples, right? So So what I'm showing you here is one way of measuring that decorrelation. So what you do is, again, you think of some orthogonal parameters, and from those orthogonal parameters, which I'm representing here with this perpendicular symbol, you can calculate a autocorrelation function, and then based on that autocorrelation function, you can get a lag time, and you can see what are the different lag for the different values of lambda naught. What does your lag time look like? And what is the average time between each crossing? And when you multiply the two, you get the time that you should have between two crossings. And so based on that number, then you can decide where to place your lambda naught, because you want to be able to sample enough number of configurations, you want them to be decorrelated, and you want them to be able to span the orthogonal direction properly, right? So when you can satisfy all of these conditions, that's the lambda naught you want to pick. And then you go through the process to get all of your sampling. And once you do that, you can visualize your system's output in many different ways. This is one way of doing it. What we are looking at here is a forward flux sampling run of, again, Lennard-Jones nucleation. In the inner, so each of the circle represents a interface. You're going from the first interface to your last interface, and every dot on this circle represents a configuration that reached that interface, right? So you start from here, you've reached at your first interface all of these configurations, then you shoot simulations, and this one is spawned two configurations for the next interface. From here, you're spawning few more, so on and so forth. We've also colored this with committer probability, which you can actually calculate for each configuration using FFS. And again, committer probabilities measures what is the probability that a given configuration will go to basin P. And if you have a committer value of 0.5, you're at the transition state. So you can see here that we get, if you just look at these straight lines, which are basically the paths connecting one configuration to the next at the next interface, you see we get a lot of lines, which basically says we've sampled statistically significant number of transition paths. And this also tells us, whether or what is the, how much each of these configurations are contributing to the configurations on the next interface. And you can also visualize this in a slightly different manner, because once you have all the paths, you also want to have ways of assessing what is the quality of your sampling, right? Are you sampling well? Should you trust this ensemble, or are there other issues in the sampling, especially when you get into systems with rugged energy landscape? for every method, that is a challenging question to answer. So one thing that you can measure in forward flux sampling is what is the diversity of the configurations at any given interface. And what you're measuring in that diversity is whether they are originating from different parents, right? So in other words, you're saying how much does the beginning configurations contribute to the later configurations, right? So here, in this case, we are looking at the last interface, and or not last, but whichever 1, 2, 3, let's say it's the fourth interface, and we're looking at what configurations at the second interface contributed to the fourth interface. And for each of these configurations on the second interface, we have the configuration colored in a different color. And then whichever configuration is coming from that particular configuration, it's colored in that color, right? So if there's a green here, and if it's spawning 5 green circles, you'll see 5 green circles. And so what you want to be able to see is a diversity of colors. You don't want to see any one color that is super dominant. In other words, you don't want one configuration to contribute all the configurations at a later interface, because then that's telling you you're not decorrelating your paths well. And here we're looking at the same interface, but now with a closer inner interface. And again, you see that there's a diversity of colors, which means that we're able to sample well. You can quantify that in this manner as well. Here you're looking at what are the different contributions, or what are the different group sizes. So we can call each of these configurations with the same color as one group, then we can calculate its size. And then we're looking at what is the distribution of those group sizes, normalized by the total number of configurations we have. And then what you can do is for any given I surface, you can do that grouping based on all of the interfaces before that surface, right? So for the 10th surface, I can look at 9th. So how many of them are coming from different configurations of 9, from 8, from 7, from 6, so on and so forth. And so then I can look at these distributions. And what you want to see is that each of the group is not dominating. So let's say all of them individually have less than 10% of the configurations. Now we are also plotting in these Baker circles the outliers, which are bigger than the distribution. I think they're in the top percentile or so. And you want to see that even that is not a very large dominant group. If all of that is true, then you're getting a diversity of paths. There are many more metrics that you can use, which we've developed over the years. And the challenge here is that there are two things. One, for realistic systems, we don't know what the right answer is in most cases, right? So there's, in your potential energy surface examples, you know what the right answer is. So you can look at any of the sampling methods, you can compare with the right answer and say, okay, it's working well or not. But for realistic systems, we often don't know. So we only can develop more diagnostics and stuff to assess the quality of sampling. The other aspect is because we don't know what is the perfect path sampling, you don't actually know which method is doing well. So we can only say, okay, each method is either giving consistent results or they're different, but which one is correct is hard to argue in systems where we really don't know the right answer. So I will say that if you guys are planning to work on these methods, we recently wrote this practical guide, which really goes over all of these diagnostics where you can assess your quality of sampling for more realistic systems where we don't know the right answer, both for replica exchange, TIS, as well as for FFS. We've included examples of well-behaved system as well as problematic systems. So, in the same plots of the grouping that I showed, we also have examples of what it looks like if your system does not behave well. So you get some ideas about that. Yeah, so this is all I wanted to tell you about FFS. And then I'm looking at the chat to see if you have questions. And also, if you have any questions, just let me know, we can answer them. So Souvik asked, how do you make sure you reached the next state? Is it by monitoring some CV? How do you define the boundaries? Yes, so it is just like we do in Redis, you have to use an order parameter that can separate state A and state B, and then you just divide that into different milestones between A and B. So for example, if you're thinking about nucleation, Or if you think, you would think about the largest solid light cluster, and you expect it to be close to 0 in the liquid state, and you expect it to be some big number in the solid state, right? And so then you just say, okay, I'm going to start with my basin, and you can run a basin simulation to see what the distribution of the cluster size would be. Based on that, you can decide the boundary of A, and then you can keep moving forward. So you say, if you know my basin is at 10, say a cluster size of 10, my next interface can be 20, 30, 40, 50, so on. What's managing the simulation, Plumid or Python? Good question, actually, Gregory. So different groups who do them do it in different ways. So Plumed can only be used to calculate an order parameter if one wants to. But when you're running this for realistic systems, often the rate limiting step becomes calculation of order parameter if it's an expensive order parameter calculation. So if the order parameter calculation code is slow, then you want to find alternatives for it. In terms of just managing them, you can manage it as crudely as, say, through a bunch of shell scripts, but you can also use Python to manage them. We have in the past, because we have run at very large scale simulations, used Hadoop to manage these simulations, and Hadoop is a software that's used, for running, actually for doing large file systems, but we were able to adapt it to use for these large number of jobs. That's a good question, Woody. In these simulations, what's the best approach for energy surfaces that have multiple minima? We'll come to that if, we have developed a multidimensional format or multidimensional forward flux sampling, and that can help. The challenge there is it becomes expensive computationally. Now, if you know what the different multiple minima is, you can do certain tricks, but if you don't know, then you have a problem. And that's what you'll see in some of the examples for the potential energy surface. All right, any other questions? If not, I'm going to stop sharing. In the meantime, I'll stop sharing. All right, so what we'll do is we'll do another hands-on activity using a Jupyter notebook for forward flux sampling, and Naomi will lead that.
Hi, everyone. Can you hear me? Okay.
Yes, we can hear you.
Okay, sounds good. I will share and get us started.
You may want to start with where they can access the Jupyter notebook and stuff.
Yeah. All right. I will start off.